One of the most important questions when you use theoretical distributions is to assess whether your values really follow a certain theoretical distribution. So let's talk about this. Let's talk about how to evaluate if your values follow normal distribution. Well, first of all, I must say that when we evaluate normality, we shouldn't say that our sample values are normally distributed, because usually your sample values, you have too few sample values, like 5 or 10 or 15, and of course it's not enough to say something about the theoretical distribution, which deals in theory with continuous infinite amount of values. So therefore, when we assess normality, we assess how likely our sample came from normally distributed population. For example, if you have like 10 glasses of water and chloride content in these 10 glasses of water, and if you check the normality of these 10 values, it means that you check how likely your sample came from population. So it means that how likely these glasses of water came from the lake where this concentration of chloride is distributed normally. So that's the basic idea. And we will learn two ways to assess normality. One is a visual way, so it's a sort of plot, and you will find out that this plot is very good for many other things. And one is a test. Okay, so let's start with plots. The plot I'm going to introduce here is called a quantile plot. Or short, you can call it cuckoo plot or QQ plot if you want. The idea is following. Let's say you have some values, x1, x2, and so on. Some, doesn't matter, weight, concentration, any biological properties, anything, okay? And these are your experimental values. So what you need to do, you need to compute two kinds of quantiles. You remember quantile, in this case we will call quantile, it's a probability to find a value equal or below given, okay? So the first, you compute the real quantiles, so experimental quantiles, which you know what to do, right? So you need some ranks like 1, 2, 3, 2, 3, 4, 5, 6, and then depending on the formula you use, you can calculate it. For example, we use this formula, 1 minus 0.5 over 6, 2 minus 0.5 over 6, and so on. So you can calculate the real quantiles, okay? And then you can calculate the theoretical quantiles, assuming that these values follow certain theoretical distribution. For example, you have 50 here. What should be the theoretical quantile if these values follow some theoretical distribution, okay? And then the idea is you make a plot. Here you have the theoretical quantiles, and here you have the real quantiles. And then, if values came indeed from a population that follows a certain theoretical distribution, the real quantiles and theoretical quantiles should be very close to each other. Sometimes, of course, depending on the sample size, they can be more extreme or less extreme, but the idea is that they should be pretty close to each other, so they should lie almost on a straight line, okay? And then the closer they to this straight theoretical line, the more chance that these values came from a population that follows a certain theoretical distribution, okay? So that's the idea. Now let me show you how it works for normal distribution, okay? QQ plot for normal distribution sometimes also is called a normal probability plot, okay? The idea is the same, but with some slight modifications. So that's the algorithm. First of all, we need to sort the values, because sorted values already gives us the experimental quantiles, right? Then the second thing, for each value in the sorted sequence, we calculate the quantile it has. We use the formula that we learned before, this one. And then, and that's where the theory comes from, we use the inverse cumulative distribution function and the calculated quantile value to get the theoretical z-score, okay? So if these values indeed follow theoretical distribution, how many standard deviations this particular value with this particular quantile will be above or below the average, okay? And then we make a plot. We make a plot, real values versus these theoretical z-scores. And this plot has the same meaning as I've shown before. If the values indeed follow theoretical distribution, the normal distribution, they should lie very close to a straight line. Let me show you an example, okay? So let's take these values. So we have a sample. This is the sample, okay? So we have 10 values, so sample size is 10. And these are real values. Let's think about the same example. So it's a chloride containing 10 glasses of water. Okay. First we need to do is to calculate the quantiles. So we have the first value, the second, the third. So we have ranks. And then we know how to calculate quantiles. We just take the rank, subtract 0.5, and divide to the number of values. So if we take 1, for example, subtract 0.5, it will be 0.5. Divided to 10, it will be 0.05. So it means that we expect that we will have 5% of the values below 44.4. And then we just repeat this for all these ranks. So we get the quantiles. Now what we do next? So we have the quantiles. So the P is 0.05 for the first one. Now, how many standard deviations this value with this P should be below the average, if indeed this is a normal distribution? So we can use the inverse CDF minus 1 for 0.05 and find how many standard deviations it should be below the average. And then that's the value. So it should be 1.64 standard deviations below the average. Then we just repeat it for every value. And then you will see that actually we have half of the values have negative and half of the values have positive because the normal distribution is ideally symmetric. So therefore, in theory, we should have half of the values below average and half of the values above average. Again, in theory, right? And then we just make a plot. So this is the one set of values, this is another set of values, and that's the plot that you see here. Okay, so these are z-scores that we calculated using theoretical normal distribution, the inverse cumulative distribution function. And these are the real values. So these are like you can think about z-scores as a theoretical quantile. So this is theoretical quantiles, and this is the real quantiles, okay? And then you can see that indeed our values, you can think about some straight line that our values sort of located around, okay? The second plot you see here, this one, is the cuckoo plot I've made using a corresponding R function. And then you can see that these two plots are identical. So indeed, when you make a cuckoo plot in R, it uses this algorithm. So it calculates the ranks, the quantiles, and then it calculates the theoretical z-scores, assuming that these values came from normally distributed population.